perhaps one of the most important things in statistics is the idea of hypotheses and hypothesis testing. So the first thing you need to think about is the hypothesis pair. You have to think about the question that you're trying to answer, and you have to construct a hypothesis pair based on that question. Now, the type of hypothesis you're going to be able to use depends on your scientific question, and that will also define the kinds of statistical tests and analysis that you can carry out on your data. So the hypothesis is a statement about the real world that can be falsified. Now, this is a bit pedantic because it suggests you can never prove a hypothesis to be true. So what a hypothesis is a model or an idea about the world. So you could have a hypothesis which tells you about the probability of finding snails. So we had an underlying hypothesis when we did the capture and release experiment, that the probability of catching a snail is the same every day and it's equal probability for each one of the snails. Now, the null and the alternate, the null always represents the status quo, the basic assumption. So if I'm testing out a new drug, what I have is a treatment and a control. So the null hypothesis is that the treatment doesn't work and there'll be no difference in the properties in the outcome variable of both the null of the control, and the experimental group. Now, if the alternate hypothesis is that there is a difference between the control and the experimental group. Now, other examples of hypotheses are, do the data fit expected values? So we do that in genetics when we're looking at Hardy-Weinberg equilibrium. Do the categories contain the numbers that we expect? That's something we do with the probabilities for looking at your fingernails. Do samples come from the same or different populations? So that's the idea of having the control group and the treatment group. Does that change the mean of the outcome variable? Now, you can also have ones where you're not looking at the mean because it's not parametric, so you can look at medians or you can look at orders. So there are things called non-parametric tests as well. And the other major group is there an association between these two variables or even more variables? Now, really, that one you are going to prove, even though from a pedantic Popper viewpoint, you can only falsify the null hypothesis. So in that case, the null hypothesis is that there's no association between the two variables. And the alternate hypothesis is that there is a relationship between the two. So once you know that there is a relationship, then obviously no relationship can no longer hold. So in some instances, because that's a binary decision, yes, there's a relationship or no, there's not, you do end up proving those particular hypotheses. And another hypothesis related to that is, can I predict y from my values of x? So that's regression, and that's fitting your curves or your lines to your data. So let's go over and have a look at the null hypothesis and the alternate hypothesis. So the null hypothesis is there is a specific relationship, so there's no difference, there's something is happening which is the existing model, our existing best idea. The alternate hypothesis is, with the data that we collect, is not consistent with the null hypothesis, so we have to reject it. It doesn't mean that it tells us what the new relationship is going to be, and it doesn't specify an alternative model. It just says that the null hypothesis is not true. So which test should I use? So it depends on what kinds of variables you're using, how many variables are measured, the kind of hypothesis you're testing, whether you've got survey or experimental data, and if the data is normally distributed or not. Now, in general, it's a good idea to try and use the tests that apply to normally distributed data, the parametric tests. Now, the reason for this is you're more likely to see a significant result. They have a greater, what we call, power if you can apply those rather than the non-parametric tests. So if the hypothesis is about does your data fit an expected ratio, then you use the binomial test or proportion test that we've seen already. You can use the chi-squared goodness of fit test. If there's a hypothesis about associations, then you measure correlations. And if you want to make a prediction of y from x, then you use regressions. If you've got a hypothesis about the samples coming from the same population and it's parametric data, then you're testing about the means and variance. So you're finding if the means and variances are the same for your treated and untreated groups. In large populations, strictly, we should use the z-test, but we never effectively do. For small populations, we use t-tests, and that's the one that we almost always use. If you're using more than two groups, then you first have to carry out what's called an f-test or a Fisher test to see the relationship between the groups. Now, if they do the samples come from the same population and it's non-parametric, then non-parametric methods don't have one general name. They have a name for each specific type of thing that you're going to do. So they're again tests about means and variances, well, they're more medians and quartile ranges. And the unpaired data version is called the Mann-Whitney or U-test, and the paired data test is called the Wilcoxon test. If you've got more than two groups, then you'd use a test called the Kruskal-Wallis test. Now, that's a standard way of looking at it by breaking down the data into the type of question you're doing. But another way of looking at it is to consider the idea of dependent and independent variables. Now, as I said, I don't like these terms because they're confusing. So I prefer to use outcome or response variable to be my dependent variable, the thing that is going along the y-axis. So in the question of height and weight, I can't eat a big amount of pizza and expect to get any taller, but I'm going to get heavier. So height defines weight. As we get taller, we get heavier because we're roughly approximate to a sort of cylinder. Now, the independent variable is the one that is specified during the experiment. It's the explanatory variable. So if you construct a table using these particular, using the dependent and independent variable concept, if you construct a table for parametric tests, so these ones based on the normal distribution, if your independent variable is discrete and your dependent variable are discrete, then normal distributions can't possibly apply, so you'd use chi-squared anyway. If you've got a discrete, as in two categories along the x-axis, so that's treated and untreated, and you're comparing the outcome variable, which will usually be continuous, a continuous mean across the y-axis, then those are z-tests or t-tests. If you've got more than two groups, and you've got a continuous mean variable, then you use this f-test, which is part of the process called ANOVA, or analysis of variance. If you've got two continuous variables, and you want to see if there's a relationship between them, you would carry out correlation, and if you want to use one to predict the other, then you would use regression. And there's a final thing that I'm just going to mention here, though we're not going to cover it, and that's if your x-axis is continuous, but your y-axis is discrete. So this happens when you have living, dead, with disease, without disease. So that is called logistic regression, and it's a very specific case. For the non-parametric case, if you've got independent variables discrete and dependent variables discrete, then it's still chi-squared. If you've got discrete in two categories against continuous, then it's Wilcoxon, which is also sometimes known as a sign test, or Mann-Whitney or U-test. You've got, for more than two categories and a continuous variable, you've got Kruskal-Wallis. If you're doing continuous against continuous and you want to know their association and correlation, then you use something called Spearman's correlation. And if we're doing continuous against discrete, then there is something called non-parametric logistic regression. But if I was not going to cover logistic regression, I'm definitely not going to cover something as specific as non-parametric logistic regression. That's way beyond the material we're going to cover here.